All right, this is exam 1 for Physics 102, spring 2016. The first questions are about charges. The up quark has an elementary charge of plus 2/3 e. The down quark of minus 1/3 e. What combination of these will make up a neutron? Well, a neutron, of course, has neutral charge or no charge. So if I have an up quark with plus 2/3 e, then I have to have two down quarks to balance that out. So the answer is B. You bring a negatively charged rod next to a neutral copper wire. Which of these statements are true? Okay, well, first of all, what happens here? I have negative charges here. That means that the negative charges on the copper wire are going to move to that end, leaving this end positively charged. That's going to cause it to be attracted to the negative rod, so A is not the right answer. Negative charges will move to the right-hand side of the wire. Okay, that is true. Nothing will happen. That's not true. Positive charges will move to the left-hand side of the wire. Okay, well, we'll come back. We'll mark that, and then we'll come back and talk to it. Negative charges will move to the center of the wire. That's not true. Okay, well, I am left with positive charges on this side of the wire. They don't actually move to that side of the wire. It's like they're left on that side of the wire so that you get an excess of charge. So faced with either B or D, I'm going to go with D. That's physically what's happening, is that the negative charges move to the right-hand side of the wire. Imagine two charges, A and B. Charge A is attracted to a positive charge B is repelled from a negative charge. What happens if you bring A and B together? Well, A, if it's attracted to a positive charge, has to be negative. B, if it's repelled from a negative charge, also has to be negative. So if you bring them together, they're going to repel. So B is the right answer. Doug rubs a piece of fur on a hard rubber rod, giving the rod a negative charge. What happens? Okay, well, I have this rod, I rub this fur on it, and it leaves a negative charge on the rod. What's happening here is not that protons are removed from the rod, but that the electrons are added to the rod. The fur, if it's charged, the fur leaves electrons onto the rod, so that means that the fur now has a net positive charge. If it was neutral before, it loses some electrons, and so the fur is no longer neutral, it's positively charged. So C is the right answer. Two electrons and a third charged particle are located at different positions along a straight line. Both electrons experience zero net force due to static electricity. Is the charge of the third particle positive or negative, and where must it be located on the line relative to the electrons? Okay, well, the answer is B. Hold on just a sec. Okay, we had a very similar question to this before, but it's a little bit different, so it may have led you astray just a little bit. But let's imagine here I have my electron here and here. And I want to put a third particle such that the force on both electrons is zero. So I'm going to tell you right now, I'll show you the answer for B. If I put a positive particle there, that means on this particle right here, I have a force in this direction. That's the force due to this negative charge. And a force in this direction. That's due to this positive charge. In a similar way, on this particle, I'll have a force in that direction due to the positive charge, and in that direction due to the negative charge. Now, that will give me a net force of 0 on the electron. Now let's look at these other ones. So let's say instead I have a negative particle in between. So if I have a negative particle over here, I'm going to have a force in this direction and in that direction, this direction, and in that direction due to those two particles. So that's not going to work. Negative with both electrons on the same side. So that would look like a negative particle over here. In that case, I will have a force due to this particle in this direction and a force due to this particle in this direction. Okay, that does give me a net zero force. However, look on this particle, due to this charge, I have a force in this direction due to this particle, and due to the negative particle in that direction. So I don't have a zero force on that one. And then finally, positive with both electrons on the same side would look like this. So this would be a positive particle. Now due to this charge, I would have on this charge, I'd have a force in this direction towards the positive particle, and in that direction from the negative particle. And on this charge, I would have a force in that direction, and then a smaller force in that direction to the positive particle. So you see no net zero force on that one. So it was tricky. You sort of had to think about it. It was a little bit different than one that we had seen before, but the answer there is B. The diagram shows three heavily charged plastic cubes. The net force on cube number 3 is shown. If cube number 3 is positively charged, what are the charges on cubes 1 and 2 respectively? Okay, so I have a positive charge here, and then in order to get this force that's often in this direction, I'm going to have a force that's in this direction and a force that's in that direction. So in order to get that, if that's positive, this has to be positive and this has to be positive. So both cube 1 and cube 2 have to be positive, so 6 is B. What is the magnitude of the force on the plus 2 nanocoulomb charge? Okay, well, first we can draw our forces. I have a force due to this negative 10 in this direction and due to this negative 10 in this direction. Now, fortunately, those cancel out. So this becomes a very simple problem because I only have a force in this direction due to the 5 nanocoulomb charge. And it's 3 meters from it. And so that force is going to be K QQ over R squared. Actually, I'll just go ahead and write out these numbers. We'll see how they work out. 9 times 10 to the ninth, 5 times 10 to the minus 9, 2 times 10 to the minus 9, divided by 3 squared. That cancels there, there, and there. And so I get 10 times 10 to the negative ninth. That's 1 times 10 to the minus 8. So for number 7, C is the answer. For the figure in the previous, what is the direction of the force on the 5 nanocoulomb charge? Well, we've already drawn that. It's along the negative y-axis. And again, this is because these two forces are equal and opposite because these two charges are identical and those two forces cancel out. The force between two charges, which are separated by 4 meters, is 12 newtons. If the two charges are brought closer by a distance of 2 meters, what is the force? So remember, force is KQ over R squared. I have my distance. That means I quadruple my force. So it was 12 newtons, now it's 48 newtons. The figure shows two metal spheres, each have a charge. If Q2 has a charge with a magnitude of 3 coulombs, what is the charge Q1? And further, I know that this is minus 3 coulombs. I know that Q1 has to be positive, so I can get rid of that one. Now I just count the lines. Let's see, here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines on there. And then over here I have 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 20, 22 lines coming out of Q1 and 11 going into Q2. So Q1 has twice the charge because it has twice the field line. So B is the answer to number 10. For this figure, what is the magnitude of the electric field at point A? All right, so I have my electric field here. I want to know its magnitude. I can draw the vectors. I have one vector in this direction. Remember, imagine a positive particle at that point and ask yourself the question, what is the direction of the force due to that negative 1 nanocoulomb charge? And it'll be to the right. And then this electric field is in this direction. I'll call this e to the 2. And this is E due to that negative 1 nanocoulomb charge. And then I want to calculate what is E1 and E2. E1 is KQ over R squared. That's 9 times 10 to the ninth, 1 times 10 to the minus 9, divided by 3 squared, KQ over R squared. The minus 9 comes because this is a nanocoulomb. Cancels, 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 cancels. That's 1 Newton per coulomb. And now E2 is 9 times 10 to the ninth, 2 nanocoulombs. That's 2 times 10 to the minus 9 coulombs divided by 3 squared. Cancels, cancels, cancels. That gives me 2 newtons per coulomb. And so I have 1 Newton per coulomb in this direction, 2 newtons per coulomb in this direction. I want to know the resultant of that. It's going to be the square root of 1 squared plus 2 squared, square root of 5, which must be 2.2. So number 11 is C. And now what is the direction of the electric field? So I want to know what is this angle. Theta is the inverse tan of opposite over adjacent, that 2 over 1. I get 63 degrees. That would be 63 degrees below the positive x. So let's see what my answers are. Oh, looks like that is an option. So B for number 12 is the answer. But remember that I could measure it from other axes. Like I could have said measuring it from this axis. So it would be like, what, 302 degrees, 365 minus 63. But that's the right answer for number 12. Electric field is force per unit charge. Consider this configuration as the charges. What point is the electric field equal to 0? And point C is equidistant. So here I have these charges. At point A, I have an electric field due to this plus 2q charge in this distance and the plus 4q in that distance. So it can't be A. And for a similar reason, it can't be E either. So it has to be B, C, or D. Notice that I drew the relative lengths of the vectors differently. This vector would be due to the plus 2q charge because it's closer. And even though this vector, the 4q charge is bigger, it's also quite a bit further away. So I can draw them relatively. All right, but those are not the answer. So let's look at B, C, and D. Okay, so B here, due to this plus 2q charge, has a vector in that direction, and it's farther away from the 4q charge, so it is conceivable that it has a vector that's the same distance. Now let's look at C. I'm going to draw it down here. Due to the plus 4q charge, it's in that direction. Due to the plus 2q charge, it's in that direction. It's half the length, and so that is not equal to 0. So C cannot be the answer. I got rid of A and E. I think it might be B, but let's draw D here. D, due to the plus 4q charge, is in that direction. The plus 2q charge is in that direction. So it's not D. Notice it's further away from the smaller charge. So now let's look at 15. Proton is accelerated by a constant electric field, 220 newtons per coulomb. What is the proton's velocity? Okay, so first we need to figure out what is the force. F is equal to Q times E. And then we'll combine these sets. We'll set that equal to m times a. So really I'm looking for the acceleration, which is going to be QE over ma. Of a proton, you need to look on your equation sheet if you don't know these. 1.6 times 10 minus 19, 220 newtons per coulomb. The mass of a proton, what is it, 1.67 times 10 to the minus 27. And actually, I'm looking, no A there. So that'll be my answer. I get 21 or 2.1 times 10 to the, see, 3, 6, 9, to the 10th meters per second squared. And now I'm looking for it after this time. I say V is equal to V naught plus AT. V naught is 0. We'll assume that it's at rest initially. So I multiply that acceleration times 1 times 10 to the minus 6. I get 21,000, which is C, 21,000 meters per second. Again, this is 2.1 times 10 to the 10th, which is the acceleration times 1 times 10 to the minus 6 seconds, which is your time, and it gives me 21,000. All right, a parallel plate capacitor initially has a potential difference of 10 volts and is then disconnected from the charging battery. If the area of the plates is now doubled, what is the new value of the voltage? Okay, so we had a question like this, but I have this potential difference of 10 volts, and then it's disconnected from the charging battery. That means that when I disconnect this, it has a charge, remember Q is equal to CV, equal to C times V. It has that charge. And now, if I change, this charge will remain constant. So the product of C and V will remain constant. And now, if I change the plates, so if I double the area of the plates, remember C is epsilon naught A over D. If I double the area of the plates, that means that I double the capacitance. So if I double the capacitance, I have to have the voltage. So where it was 10 volts, now it has to be 5 volts. So B is the right answer. Parallel plate capacitor is these dimensions. They're separated by that amount of thickness of paper. So you have these two plates, and then they have this paper in between them. That's that distance. And I want to know what is the charge that can be stored. Now, I know that charge for a capacitor is equal to C times V. So I first need to find C. C is kappa epsilon naught A over D. Remember, kappa is not the same as K. Kappa is a dielectric constant. It's 3.7. Which was it? 8.85? Let's forget this constant. Let's look it up just to be sure. You should have your equations. 8.85 times 10 minus 12, I think. Yeah, 8.85 times 10 to the minus 12 is our permittivity of free space. A is going to be 0.04 times 0.05 divided by D, which is 1 times 10 to the minus 3, so 1 millimeter. And then that'll give us our capacitance. I get 6.55 times 10 to the minus 11. Right, 655 nanofarads. So that's my capacitance, and now I want to know the charge. Q is equal to C times V. This number times 1.5. I get 9.8 times 10 to the minus 11. So E is the right answer for number 17. Inserting a dielectric between two charged parallel conducting plates originally separated by air and disconnected from a battery will produce what effect on the capacitor? So all this stuff is disconnected from a battery. Is say that there is no charge on it, that I just have these two plates and I'm sticking this paper in between the two plates. What happens? I'm not increasing the charge. I don't change the charge because it's not connected to a battery. It cannot either add charge or take away charge. I can't increase the voltage of the capacitor either because it currently has no voltage at all. Actually, hold on just a second. Let me pause this. I'm sorry, let me rephrase that. I was misleading just a little bit. There is charge on these capacitors. So I have these two plates that have charges on them, but they're not connected to a battery. So similar to that previous problem where we disconnect the thing from the battery, and then I come along I add this dielectric in between them. Now the dielectric will cause the capacitance to increase. So I know 3 has to be one of these. But will it also cause the voltage to increase? Well, let's think about this. I know that if Q is equal to CV, if Q remains constant, as it must, if C goes up, then V goes down. So if this was to say decrease the voltage of the capacitor, then that would be a correct answer. But it doesn't. It says increase. So the combined effect of adding the dielectric is to increase the capacitance and decrease the voltage. That's not an option. So 3 only is the right answer. And it doesn't decrease the capacitance of the capacitor. It does the opposite. All right, number 19. This shows a collection of charges. At what point is the potential equal to 0? All right, well, the potential is equal to 0 when you're equidistant from equal but opposite charges. So here, the potentials of these two charges cancel out. The potentials of these two charges cancel out. And the potentials of these two charges cancel out because this point A is equidistant from all of those various charges. Now, I'm going to go through all these points, but just show you, like for example here, the distance between these two charges is equidistant. Oh wait, yeah, no, this, I will go through them all because the potential here is all equal to 0. The potential here is also equal to 0. All right, so we have A and B, so you probably already guessed that E is the answer, which it is. But let's go ahead and do C and D. C, the potential due to these two charges, that cancels out because I'm equidistant from those two equal but opposite charges. Similarly there and there and there and there. I'm equidistant from all those charges, and then that's also true for point D. So E is the right answer. Which of these is the unit for electric potential? Well, remember, potential is KQ over R squared. You can start with it there, or excuse me, KQ over R. You could start with it there, but an easier way of thinking about it, well, potential is energy per charge. right? Energy per charge. So that's energy per charge, but we also know the potential is measured in volts. So it could just be 1 and 2. But let's also think about, is it this one as well? So we're not sure about that. We see the per unit charge there, but is this energy? Well, we could go back to our 1/2 mv squared. All right, 1/2 mv squared is kilograms meters squared per second squared. All right, it looks like 3 then is not that. So it's just 1 and 2. So number 20 is B. Let me pause for just a sec. Okay, I had intended for the answer to be E here, which in order to make that, this has to be second squared. So on your test, the answer will be E, and you'll have a second squared here, in which case, these are the units. That's energy, and then per unit charge, and this is the same as what we have here. Now also let me show you, let me clear this up a little bit, because we can also start with our basic expression for electric potential KQ over R. And this can also give it to us. Now, K, if you look on your equation sheet, is Newton meters squared per Coulomb squared. And then we have Q, which is in coulombs, and R, which is in meters. That cancels there. That cancels there. So I'm left with Newton meters over coulombs. But a Newton is a kilogram meter per second squared, mass times acceleration. Then we have another mass, and then we have a 1 over Coulomb. So that's kilogram meter squared per second squared over Coulomb. Which will be the same, you'll have a 2 here, will be the same as option 3. All right, so a couple different ways you could approach that. For this scenario, where is the electric potential the least? All right, remember electric potential is KQ over R. If R goes up, V goes down. So it's out here at this most distant. So it's A and D is the potential is the least. The electric potential 1 meter from a certain charged particle is 4 times the potential at 1 meter from a second particle. How do the particles' charges compare? Okay, so V is KQ over R. Looks like I'm 1 meter. Both of these, I'm 1 meter from the same, or from 2 different particles, but on one of them, I have 4 times the potential. And so the first particle, if it has 4 times the potential, it has to have 4 times the charge. So the first particle has 4 times the charge of the second particle. If the distance between 2 negative point charges is increased by a factor of 3, then the potential energy is what factor times the initial potential energy? Well, potential energy, remember, is KQQ over R. I'm increasing the distance by a factor of 3, so my potential energy goes down by a factor of 3. So D is the right answer for 23. And then here, what is the potential at point A? Well, I know that these distances are 5 meters, and I do the voltages of the negative 10 and just add that up to the plus 5. That's going to be 9 times 10 to the ninth. Q is negative 10 times 10 to the minus 9 over 5 plus 9 times 10 to the ninth, 5 times 10 to the minus 9 divided by 5. I can cancel some things out there, and there, there, and there, there, and there, there, and leave me a negative 2. So I get a negative 18 plus 9, which is negative 9 volts. So A is 24, and then 25. What is the potential energy of that charge configuration? Well, potential energy is KQQ over R. How much energy is contained within that configuration of charges? That's 9 times 10 to the ninth. Let me see what those charges were. 10 and 5 nanocoulombs. And then they're separated by a distance of 4 meters and 4 meters, so 8 meters. And let's see, canceling and canceling. I get 1 times 10 to the minus 7. Oh, but one of these was negative. 10 coulomb, 10 nanocoulomb, so I have a negative 1 times 10 to the minus 7. So E is the right answer for number 25. That's the end.